All right, hi everybody. This is the last video on this set of notes. We previously talked about Lewis structures in the first video. We talked about Vesper 3D structures in the second video. Now we're going to talk about electronegativity. We're going to talk about polarity, both in bonds and molecules. And then we'll do just a quick little blurb on solubility. Okay, so let's start with electronegativity. You can kind of guess what that word means. So I would recommend that you write down the definition. It says electronegativity is a measure of the tendency of an atom to attract a bonding pair of electrons. If I were going to put this in words that maybe make more sense for my students, I might say electronegativity is how strong an atom is. An atom that is really strong will pull electrons toward it, and an atom that maybe isn't as electronegative, isn't as strong, won't be able to hold on to the electrons with quite as much force. So I do suggest that you write a few things down here. So I'm going to recommend that you draw this line somewhere in your notes. So it's a number line, and I want it to start at 0 and end at 4. And then you're going to have, so pause me at any time that you need to, you're going to have a divider at 0.4. And then you're going to have another divider at 1.7. And I see that it's not very evenly distributed, but whatever, it's good enough. And then we're going to add some labels to it. So you're going to use what's called so go ahead and be drawing while I'm talking. You're going to be using something called a table of electronegativities, and you're just going to find the difference between two atoms. One is stronger, one is weaker, and you're going to look for the difference between them. And the difference is going to tell you whether this molecule is covalently bonded, polar covalently bonded, or ionically bonded. Kind of a funny word to say, ionically bonded. Okay, so what I want you, now that you have the number line drawn, I want you to label. So between 0 and 0.4, I want you to write nonpolar covalent, and that the electrons, I always abbreviate electrons as E negative, the electrons are shared equally. So nonpolar covalent, electrons shared equally. In this middle section between 0.4 and 1.7, I want you to write polar covalent, electrons shared unequally. And then in the last section, write ionic bond. And this is where we're not sharing electrons anymore, where we're actually transferring electrons. One electron is handed to a different atom, and that different atom accepts the electron. What you should be aware of is that this is a continuum. It's not an automatically, this is when a covalent bond is, automatically this is when a polar covalent bond is, and automatically this is when an ionic bond is. You can have stronger or weaker ionic bonds, and you can have stronger or weaker polar covalent bonds, depending on where they fall on that continuum. And so the labels are a little bit arbitrary based on what scientists have kind of discovered. They're kind of giving us sort of okay, if it's at a 0.4, we're going to say that's the line between polar and nonpolar. Okay, so it's a continuum. All right, so it says if the electronegativity values between two atoms involved in a bond are the same, then what we have is a covalent bond. So let's say you have a bond between two hydrogen atoms. And hydrogen atoms, I'm going to switch screens for just a second. This is the table of electronegativities, and you can see that hydrogen has a 2.2. So if we find the difference between one hydrogen atom and another, 2.2 minus, difference means subtraction. So 2.2 minus 2.2 is 0. So if their electronegativity is the same and we have a 0, notice it's down here on the number line, and it says this is a covalent bond. It's a covalent bond. They are sharing the electrons equally. Now, there are other atoms, if I go back here again, there are other times where it doesn't have to be two of the same atoms. It could be two different atoms. But if they have similar electronegativities, so they're both kind of equally strong, they're going to share that electron equally. We'll pretend like it's like two children sharing a toy. And to be fair, they're sharing it 50% of the time. One child has the toy 50% of the time. The other child has the toy 50% of the time. We say it's fair, and that's a covalent bond. All right, so now the next one, if the difference between the two, if one of the atoms is a little bit stronger than the other, but not super strong, then we call that a polar covalent bond. Sometimes in my analogy of the children sharing a toy, sometimes I say it's like one of the children is a little bit stronger and is a little bit of a bully. And instead of sharing that toy 50-50 with the other child, maybe the bully is taking the toy 60, 70% of the time, and the other child is losing the toy and only has the toy about 30% of the time. That's an analogy for a polar covalent bond. What it means is that one atom that is a little bit more electronegative, a little bit stronger, is pulling the electrons closer to it, giving it an overall negative charge. Who has ever met a bully that didn't have a negative attitude, right? So overall, that stronger atom that's more electronegative, it's going to bring the electrons toward it a little bit closer, and it gives it a partial negative charge. And we're going to talk about that in detail. Notice that there's this little sign right there, that little symbol. That's a partial negative sign around the atom that is a little bit stronger. And then the atom that doesn't get the electron for as much of its time or as closely, we're going to say that one has a partial positive charge. Now, if we go all the way the other end, if we have two atoms that are bonding that are very different, one is super strong, the other one is not, it is as though it's a child that just handed a toy over. And the bully has the toy. There's no sharing happening. That bully has the toy. So in this case, an ionic bond, the electron has been handed over. So now there's one atom that has the electron and one atom that does not have the electron. So that's what electronegativity is. And you're always just counting the difference. You're subtracting the two. Very important that we notice this little by the way at the bottom. An ionic compound, so anything between 1.7 and 4, is defined as one that can transfer an electric charge. Sometimes calculating electronegativities can give misleading information. If a substance can transfer an electric charge, it is ionic, even if the differences in the electronegativities would say that it's a polar covalent or a covalent compound. If it can transfer a charge, it's ionic. So that's the metal and nonmetal, that's the ion. So really the table of electronegativities is more for the covalent compounds. We're trying to figure out, are they sharing equally or are they sharing unequally? That's really what a table of electronegativities is useful for. Okay, moving on. So comparing electronegativity differences, you use your table to determine the difference by subtracting them. And then we already wrote these things down. If the electronegativity difference is greater than 1.7, we're going to say it's ionic, or it can transfer a charge. If the difference is between 0.4 and 1.7, we'll say that's polar covalent. And if it's between 0 and 0.4, we'll say that's straight up sharing and covalent bond. And then this image is kind of useful for looking at the difference between sharing unequally, and actually taking of the electrons. Okay, so now water, it turns out, is phenomenally important on this planet. So we need to spend a little bit of time talking about water specifically, and it comes up in AP biology as well. What types of bonds are found in water? Well, let's do the math. So let me hop back a couple slides. Let's look at that math. We have H is a 2.2 and O is a 3.44. Hey, by the way, sometimes the tables of electronegativities that you find online are subtly different. So don't panic if my numbers are a little bit different than yours are. So we're going to subtract 2.2 and 3.44, and we get about a 1.36. Did I do that math in my head right? Which leads us to, that would be a 1.36 would be in this category here. So the bonds in water are polar covalent. So you need to write that down. I would write down the bonds within water are polar covalent. So water is incredibly important. You don't need to write this down, but water allows life to exist, and scientists who are searching the universe to try to find life on some other planet, we're pretty sure that life won't exist anywhere that doesn't have water. Why? What makes water special, and what are some of its characteristics that are so unique? Well, first, water is a liquid instead of a gas. Other molecules that have a similar mass to water are gases. So why is water a liquid? Well, it turns out water is attracted to itself. That'll make sense soon. Water has a really strong surface tension. Ice, the solid form of water, floats on its liquid form. That might be obvious to you. You've seen ice float, but that's a little counterintuitive. Solids are usually denser than their liquids. So solids typically sink. So it's very interesting and life-giving. It allows life to exist in oceans where there is ice on top. They can be isolated and insulated below. Water has a very high specific heat, so it doesn't heat or cool rapidly. Thank goodness. Our planet is what, somebody can correct me, 80% water, something like that. Because we have so much water, the carbon dioxide that we're adding to the atmosphere that's heating the planet, it's heating the planet more slowly because we have these giant oceans that slow the process of heating. And thank goodness for that. Water can climb within a tree, and that has to do with the fact that water is all of this has to do with the fact that water is attracted to itself. Have you ever thought about how water moves from the roots of a tree all the way up to the leaves of a tree? Have you ever tried carrying even a gallon of water? It's heavy. Trees don't have muscles, they don't have hearts. How is it that the water is moving upward? It is an amazing, fascinating process that scientists are only now really being able to figure out. And it's all because of water's polar covalent nature. And so we think that life on this planet and life anywhere in the universe requires water. Okay, so next thing that I would recommend is that you actually draw this picture. Let me get my picture out of the way. Put me over there. I'm going to recommend that you draw this picture. Hey, everybody, there's a spider on the ceiling, and I'm afraid of spiders. So I'm going to keep staring at it once in a while to make sure that it isn't crawling over my head. Because if it crawls over my head, I'm going to have to stop this video. Do you all want to see this? Okay, can you see this? Nope, you can't quite see the spider. But once he gets here, I am running for my life. Okay, so hopefully you've been drawing this picture while you're listening to me being afraid of spiders. I respect life, by the way, so I'm glad we have spiders. I just don't want them over my head or landing on me. So you're going to draw this. This is a picture of water. So there's an oxygen atom. Oxygen is the bully here, everybody. Oxygen is the more electronegative atom. It is bonded to two hydrogens. Remember that it's bent. We learned that in previous notes that we were taking. The blue spheres represent the electrons that they are sharing, and the electrons are being pulled closer to the oxygen than they are. Oh no, I don't know where the spider went. It's not there anymore. Seriously, you guys, there's a spider crawling around. Oh, I'm grossed out. Okay, sorry. Moving on. So the oxygen is stronger, and so it's slightly negative because the electrons are being pulled closer to it. So notice that it says partial negative charge, and then we use this symbol. It's a delta. It's a lowercase delta, which is a Greek letter, and we put a little minus sign to indicate that the oxygen atom is slightly negative. On the opposite sides of the water molecule are the hydrogen atoms, and those guys are losing the electrons. They still are holding them, but not, sort of 50-50 the way we talked about a child sharing. And so we show them having a slight or partial positive charge by showing the Greek letter delta with a plus sign by it. So this means, interestingly enough, this is what gives water its amazing qualities, that the partial positive of one hydrogen atom, so imagine this hydrogen atom right here, is slightly attracted to the partial negative of an oxygen on a different water molecule. So if we have two water molecules, they're going to position themselves so that the hydrogen of one water molecule is close to the oxygen of another water molecule because they're partially negative or partially positive and partially negative. So that's called a hydrogen bond. We're going to learn a lot more about hydrogen bonds in AP biology, but they are important bonds that give water this amazing polarity and amazing characteristics that it has that other things don't. All right, so now we need to be able to talk about the difference between polar bonds and polar molecules. And this, I think, is the most intellectually complex. I don't see this writer. Intellectually complex topic that we have in this set of notes. So we've been calculating polar bonds at this point. So give me a second here to move me. Where's a good place to move me? We'll try over there. So it says, use the table of electronegativities to determine if a single bond is nonpolar covalent, polar covalent, or ionic. So those are polar bonds. So if we look at this molecule right here, the hydrogen and the chlorine, the hydrogen is weaker and the chlorine is more electronegative. So when we draw, we're going to draw this arrow that's called a dipole arrow. You point toward the bully. You point toward the more electronegative atom. And then you put a plus sign on the end of the arrow nearest the weaker or the slightly positive atom. So that's an example of a polar bond right there, just between hydrogen and chlorine. But now the question is, what about the entire molecule? This requires something called vector analysis, which most of my students haven't had in math class yet. So instead of doing some of the math that's involved in vector analysis, I'm just going to ask you to learn some things and accept them as truths. And once you get to that level in math class, you can see why those truths are true. I'm going to give you an analogy and see if this can start to make some sense. So this is a terrible analogy. It's very limited, but see if this will help. Imagine that you have two people playing tug of war, and you have a little ribbon in the middle of the rope that, if it moves one way or the other, indicates who the stronger person is. If you have two people on either end of the rope that are exactly the same strength, what's going to happen to the little ribbon on the rope? Nothing. It's not going to go one way or the other, because the two equally strong people, they're pulling and pulling and pulling, is going to cancel each other out, and that ribbon is not going to go to the right or to the left. So that's what we're talking about with this vector analysis. Sometimes the pull one direction or the other cancels out, and we end up, even though they're polar molecules, polar bonds, we end up with a nonpolar molecule. Nothing happens because they cancel each other out. So these are things that you're just going to kind of have to memorize and get the hang of. So let's see if we can say this. It says, use the symmetry of the molecule to determine if the molecule as a whole is polar or nonpolar. Now, in my class, I asked you to learn 4 shapes. You needed to know linear, bent, trigonal pyramidal, and tetrahedral. So it turns out that linear and tetrahedral are symmetrical molecules, and bent and trigonal pyramidal are asymmetrical molecules. So asymmetrical molecules, they can't cancel each other out. So let's read what it says here. It says, if polar vectors cancel each other out, the molecule as a whole is nonpolar. So a symmetrical molecule, what counts as symmetrical? Linear and tetrahedral sometimes. The only time linear and tetrahedral are symmetrical is if their terminal atoms are the same. If their terminal atoms are different, then we're no longer symmetrical. So a symmetrical molecule that contains polar bonds is a nonpolar molecule because the vectors cancel each other out. It's like two equally strong people pulling on that tug of war rope. Let's try this. I'm going to move my image around again to get it out of the way. Let's try down here. Okay, so it says trigonal pyramidal is always asymmetrical. That's this one right here. So the molecule is automatically polar if there are any polar bonds. If there's no polar bonds, the molecule is nonpolar. Let that sink in. If there's no polar bonds, the molecule is nonpolar. The question is it ever, if it's got polar bonds, is it ever nonpolar as a molecule? That's what we're trying to figure out. Okay, so trigonal pyramidal, if there's polar bonds, it is automatically polar. They never cancel each other out. Again, this is an asymmetrical molecule. Now, it's tetrahedral, but notice that the terminal atoms are not all the same. So this is considered not symmetrical because the terminal fluorine is different than the terminal hydrogens. So there's one polar bond in this case that's pulling strongly one direction, and the others aren't as strong. So this is a polar molecule. Now let's take a look at the tetrahedral that's right below it in this diagram. This one is symmetrical because all four of the terminal atoms are the same. They're all equally as strong. Imagine a rope. This is a very flawed analogy, but imagine a rope that has four different ways people can pull, and all four of them are equally as strong. In that case, it is because it's a symmetrical molecule and they are pulling against each other, they cancel each other out, and the molecule is nonpolar. Polar bonds, symmetrical molecule, nonpolar. That one takes a little bit. Let's try it again. So bent and trigonal pyramidal are always asymmetrical. The presence of polar bonds makes these asymmetrical molecules polar. They are polar. If there are any polar bonds, these molecules are polar. If there are no polar bonds, then the molecules are nonpolar. That's not an issue. Okay, let me get my picture out of the way. Let's go up here. So it says linear and tetrahedral are symmetrical if the terminal atoms are the same. If the bonds are nonpolar, the molecules are nonpolar. But this is the one that's tricky. If the bonds are polar and the molecule is symmetrical, then the molecule is still nonpolar, even though the bonds were polar. They canceled each other out. Okay, that is probably intellectually the hardest thing to absorb in this unit. So take some time to think about that. Okay, everybody, I'm going to skip over the electron density maps, and we're just going to wrap up by talking a little bit about solubility. It's just going to take us a minute here. So it says how solutes dissolve in water. Remember that water is polar covalent. This is really important. So how solutes, the things that dissolve in water, how they dissolve depends whether they have covalent bonds or ionic bonds. So sugar or sucrose is covalently bonded. So when it dissolves in water, it stays in its same structure. Its covalent bonds stay together. But when an ionic molecule, that's not the right word, an ionic compound dissolves in water, it actually gets pulled apart. And I'll make that make sense. So it says when sugar, a covalent molecule, is added to water, the sugar molecule stays together, the whole thing. So we still have sugar molecules that are evenly distributed throughout the water. When salt, which is ionic, so it's a positive Na plus, a positive Na, and a negative Cl, when it's added to water, the Na and the Cl get pulled apart and the water molecules get pushed in between the two of them. So let's look at this a little bit more visually. So here's a little compound of salt. So notice that the NAs are next to the Cls and the Cls are next to the NAs all the way around. But now we're trying to dissolve it in water. This is tricky because water is polar covalent. Remember, the oxygen has a slight negative charge, so it's going to be attracted, that oxygen is going to be attracted to the positive charge on the sodium. So the heads, is that the right word? I don't know. The oxygens on the Mickey Mouses, the chin of the Mickey Mouse. There we go. If water looks like a Mickey Mouse, the chin of the Mickey Mouse, which is the oxygen atom, is going to be attracted to the sodium ions. But vice versa, the ears of the Mickey Mouse, which are slightly negatively charged, they're going to be attracted to they're slightly positive charged. They're going to be attracted to the negative charge of the chlorine, and they're going to separate. Each sodium is going to be surrounded by the oxygens of water, and each chlorine is going to be surrounded by the hydrogens of water. And so the sodium and the chlorine are going to be separated. That process is called dissociation. You might want to write that down. Dissociation, to dissociate, is the process of ionic bonds being split when they're dissolved in water. And then I don't know how important this is, but just an FYI, you may have heard of electrolytes. So electrolytes are chemicals that dissociate into cations and anions in water. Remember, cations are positive, anions are negative. A strong electrolyte completely dissociates, and a weak electrolyte has partial dissociation, but not the entire thing dissociates. Okay, everybody, that was a long set of notes. We are all done. Please let me know if you have any questions. Have a great rest of your day.